Okay, I think we should get started. So just a few announcements. There is a lab due next week. Okay. I will make sure that the TAs are available for help. So go to office hours if you have questions, ask questions on Piazza, anything we can do to clarify what is actually being asked. We're happy to help with that. Okay. So that's due next week. And then once that is done, we will hand out a couple more lablets. I think we are in the midst of doing the cloud computing lecture. So there's going to be a lablet on cloud computing. There's also a lablet on virtualization that I haven't yet handed out because there's already a lab due. So I'm going to hand those out once the lab comes in. Okay? And you'll be using those concepts for the final lab, which is due a month from Monday. All right. Okay. So without further ado, let's get started. So last time we were talking about cloud computing. Okay. I ended with this picture. So essentially, cloud platforms allow you to lease or rent IT resources like server, storage, network bandwidth, and so on from a cloud provider. So what this allows you to do is you can host your IT applications, web services, whatever applications you have on someone else's infrastructure that you have leased. Okay? So you don't have to own the infrastructure. So the upfront investment you have to make to host large applications or small applications for that matter is very small. You don't need to buy anything because everything is leased. That's the first advantage. The second advantage is that you can request resources on demand. So if you need more resources, you can just ask and they get provisioned very quickly in a matter of minutes. And if you don't need resources that you previously leased, you can give them back and you are only billed for what you use, okay? Which is another big advantage. So many advantages of using cloud computing models. And what I was talking about last time when we ended was different flavors of cloud platform. Okay, so there is infrastructure as a service that is also called there's an acronym used for that, which is called IaaS. Okay, so that's an IaaS cloud. So in infrastructure as a service cloud, you are renting bare-bone resources like servers and disk. Okay, and then you as an application developer can do whatever you want. You can install any OS you want, any application software you want on the resources you use. Okay? So this allows you to rent raw infrastructure. Okay? Then there's platform as a service where you essentially have a platform that is already designed by the cloud provider to run applications. So you just write your code and you deploy it. You don't have to worry about requesting servers and things of that sort. It's the cloud provider's job to determine which servers it's going to run on, how many servers. All of that is decided for you. So you don't need to worry about provisioning resources, how many servers you need, or anything like that. Okay, so it makes the use of cloud more convenient. So you just have to deploy applications code on the platform. Okay, and at the very top, you have software as a service or SaaS clouds. So here you are essentially getting an entire application that's pre-configured. So all kinds of applications are now hosted on the cloud and offered as a service. Okay, so you can essentially, rather than buying the software and installing it on your own machines, you just go to a cloud provider and they are already have that software running and you just get credentials on it and you access it. Okay? Everything from, as I was mentioning last time, Google Mail, any cloud-based email services, cloud-based documents, all of that falls under this category. And there are many different types of business applications that are also being sold this way. So rather than buying software, you are essentially now renting software and paying based on the number of users. Okay, so 3 flavors. So we are going to go into a little more depth into the bottom 2 today, but we'll not talk really about software as a service clouds. Okay, so let's talk about IaaS cloud. So there are many flavors, not flavors, rather many providers that allow you to get resources that are virtual machines or disks Amazon has their Elastic Computing Cloud, also called EC2. Microsoft has Azure. Google has Google Cloud. And there are many more. There are many cloud providers. All of them essentially rent you servers and storage. Servers are not necessarily physical servers, they're virtual servers. And there are cloud providers that also rent bare metal machines, which means if you want physical servers, you can rent them as well. But by and large, the standard offering for cloud providers is to give you a virtual server, which is essentially a virtual machine they have created for you on their data center. So it uses virtualization to share the server resources with multiple customers. You can have more than one VM running on the server. The servers run type 1 hypervisor, so you can create multiple VMs. Each VM could have been offered to a different user or different customer. So multiple users or customers are sharing physical resources. You get large economies of scale because the prices tend to be fairly low. You can get servers for pennies an hour in many cases, and you can create them on the fly. You can request a server from any of these providers, and they can provision it for you in a matter of seconds or minutes. So you can get servers very quickly this way. This table is a little old, but it gives you the basic idea of different flavors of servers. So when you say you want a server, you got to specify what configuration you want, because they come in all kinds of sizes, and they have names associated with them. So you can have a small instance which can have one core and some number of memory, some amount of memory, some disk. You can go medium, large, extra large. There are extra large with GPUs. There are all kinds of configurations you can get. Literally dozens of different configurations have been pre-created, and they have a different price associated with it. So this one is 2 cents an hour, and that's one. The medium one is 17 cents an hour, and so on. And there can be some few dollars an hour. So the price is going to vary based on the size of the server you are leasing. Typically, they are billed by the minute, sometimes billed by the second of usage, from time you start to the time you stop and terminate your instance. And there are some storage associated with it that could have a cost based on the size of storage. Bandwidth is also billed based on the amount of data you are sending or receiving from the internet. So that's how you are going to be leasing these resources. That's your IaaS cloud. And there are many flavors of this as well. So what I showed you was the configurations, which is essentially how large a server you want. But the billing model that is offered also gives you different flavors. The simplest one is called on-demand instances. That's the default model. On-demand essentially says you provision on the fly. You can ask for servers at any time. You can give them up at any time you want, and you're only billed for the time you held the server. So essentially, you keep them until you're terminated, and you pay for the amount of time you had the server. That's on-demand instances. Now, if you want servers for longer periods of time, there is a better model than asking on-demand, which is called reserved. Reserved instances essentially say, I want servers for longer duration. So effectively, you get a discount just because you're asking for a server for maybe 1 year or 3 years at a time. As opposed to just getting it for 1 hour. So if you get it for short periods of time, essentially the price you pay on-demand price is higher. Reserved servers, because you make an upfront commitment to holding the server for at least a year, if not longer, you essentially get a discount on that price. So that's called a reserved instance. And then there are something called spot instances. Spot instances are the cheapest of the three. They look like on-demand instances. You can ask for a server of a certain size and say, I want a spot server, and you may or may not get it. So the reason is spot servers are essentially excess or idle capacity in the cloud data center that is sold off as a discount. In the old days, you could actually bid for the server saying, I want a server and this is what I'm willing to pay. It's like the Priceline model. If you actually use Priceline to buy a airline ticket or hotel booking, you said, I want a room, and you said, this is how much I'm willing to pay. The provider can say yes or no, depending on how much excess capacity there So you can get these servers at highly discounted prices. In the old days, you actually put a bid, okay, which was much lower than the on-demand price, which could be accepted or not accepted. Now you don't put a bid, but there is a price that is actually much lower that you get it at. Okay? So it's all excess capacity that you can that the cloud provider can sell at a discount. Okay? And the idea is there are users who might not be wanting to pay the full price. They're willing to wait until some excess capacity is available, and they can use that for running some jobs on the cheap. Okay. Now, the one difference between spot servers and the other two is that spot servers are preemptible or revocable, okay, which means that the cloud providers can take them back when the demand comes back. So they're not guaranteed like on demand or reserved. In those two instances, once you get the server, you get to keep them for however long you want, and you are the one, as a application provider, you decide when you don't no longer need the server and terminate it. Okay? That's not necessary in spot servers. In spot servers, the server can be taken away from you if the regular users come and ask for those servers, and then there's extra demand for on-demand, more demand for on-demand or reserved instances, then these servers become revocable. So you always have a risk that you may not get to keep the server for as long as you want. Okay? So that's the price you pay for getting these machines at a much cheaper price. So they're often available at 1/10 the price of a full server. Okay? So much cheaper. That clear? Any questions on this? Okay. So that was IaaS cloud. The next one is PaaS cloud. So here we are no longer requesting resources in terms of servers or disks. You are essentially thinking of your cloud platform as a way to deploy your application, and the cloud provider is going to decide how much resources to allocate to it based on the workload that the applications. Okay? So the cloud provider will automatically decide how large a server to give, whether to give more resources or less resources, and application developers are built not now based on the amount of time a server is held, because there's no servers you're renting, but you can be built based on the number of requests your application was served and things of that sort. So the billing model is different. You are going to be billed by workload, not by resources. Okay? And you can have different platforms that cloud providers can give you. You can have a Python platform where you can deploy Python code, or Java platform, .NET, all kinds of platforms exist where you can go and deploy this code. Okay? So in this case, the cloud provider will do what is called as auto scaling for you. Auto scaling simply means that the number of resources allocated to your application is scaled up or down automatically by the cloud provider based on the workload they see. If the workload goes up, the cloud provider will increase the number of servers allocated to your application. If it goes down, it will scale it down. Okay? So auto scaling is an important functionality that cloud providers present. It's also there in IaaS clouds. Okay? But you as an application developer have to write code that is auto scalable, because you are the one renting servers. So your application has to be written so that it can be scaled up or down. In this case, the platform will do this for you. Just give them the code, they'll just run it on multiple machines, and there'll be a load balancer that essentially forwards request to one of your many instances. Okay, is that clear? All right. So users don't need to provision manage servers, so it simplifies things. Okay? Now there's one flavor of a PaaS cloud, which is called serverless computing, that has become popular. So I'm going to talk a little bit about serverless. Okay, I don't know if any of you heard of this term. Okay, so first let's try to understand what does this mean. It doesn't mean that there is no server. Okay, despite the name, there is a server because your code has to run on something. But what it means is, from the application developer's perspective, you don't actually deal with servers in the cloud or anything like that, because at the end of the day, it's a PaaS platform. You're just going to give them code, and then the platform will run the code for you. Okay, and hence the name serverless. Okay, yeah. So it's the same as a PaaS platform with some differences. So application developers are going to deploy code on the platform. It eliminates the need to provision servers, and the cloud will take care of provisioning resources. Okay. Now, there are a few differences. Okay, in a serverless platform, the cloud provider has the ability to scale your application down to 0 resources. Okay, which means that if your application does not see any requests, they are going to not have any virtual machine running that is running an idle version of your application. So you can do what is called scale down to 0, okay, which from the application provider saves money, because if your code is sitting idle, why should they have something running on their server and take up resources? So they can scale you down to 0. Okay? That's not the most important difference. The most important difference is the way you actually write code for serverless platforms. And this is done using what is called function as a service, or FAS-based code. Okay? So in function as a service, okay, it's a different way of writing your application. Okay? You already know what multi-tier is. Okay? Okay, so we went from monolithic architecture to multi-tier architecture, where your application had tiers, and the tiers were essentially made your application modular. Okay? And then from multi-tier, we looked at microservices, where each tier could have smaller components. Each of them was a microservice, and these microservices talk to one another. That was even more modular. Okay? If you take that to the limit, you are going to end up with what is called a function as a service architecture, where you are writing code as small functions, not even a microservice. They are small functions. And you take a bunch of functions and you chain them together to get your application. Okay? So you're now starting to write code in an even more granular or fine-grained manner than what you have in microservices. Okay? So think about, you to look at your code and you look at small methods. Don't have to be small, they could be larger methods, but you have methods or functions. Okay? And you have functions you deploy on this platform. Each function has an interface that you can use to invoke it. Just as there are RESTful interfaces to invoke a microservice, your function has an API that is used to invoke it. Okay? And functions can themselves call other functions that you also written. Okay? So you now have your application written as a set of functions. Okay? Each function has an interface. The interface could be an external interface, or outside users can call your functions, or one of your functions can call another function to do whatever task your application is to do. Okay? So you have written your code in very fine-grained chunks, and you deployed them on this PaaS platform. And each function can be scaled up or down, depending on which functions are compute intensive, which ones are not, which functions are seeing high workload, and which ones are not. And the platform will do all of that for you. Okay? So different way of writing code altogether. It's become very popular. Okay? There are lots of applications that are now written as FAS applications. You don't even use microservices. You write functions and you just deploy them on the cloud. Your functions will then essentially execute whenever requests come in. A set of functions execute, do the work, send back the reply to users and things of that. Okay? So that's an example of a serverless platform that is essentially, at the end of the day, a platform as a service cloud. Okay? Though this has become a very popular way of deploying code on cloud platform. Okay? I'll say one more last thing and then stop here, which is that Amazon has something called lambdas. Okay? Lambdas are essentially functions. Okay? If you AWS Lambda is an example of writing a FAS application, because a Lambda is a function that you invoke, and then it can essentially invoke other functions and things of that. So if you've ever seen any AWS Lambdas, that's an example of serverless computing. Okay. Yes, question. Okay. Question is, what does scale down to 0 mean? Does that mean it cannot take any requests at all? So if you are currently scaled down to 0, there is no container or VM that is running that has your code executing in it. Or it's like all the containers have been paused and saved to disk. Okay. Now, while you're scaled to 0, obviously nothing can happen. Okay. But if a request for that function comes in, okay, the platform will spin up new containers and then they will execute. Okay. So, but that might take a small latency to restart, but the point is that you can always start up new containers or scale it up and so on, but you can go all the way down to 0. That's what it means. Okay. Any other questions about serverless? All right. So let's continue. I'm going to talk now about what are called hybrid clouds. So whatever we've been talking about, okay, which is Amazon EC2 cloud or Microsoft Azure, Google Cloud, they're all called public clouds. Okay, because by public cloud, it essentially means that anyone can go and create an account and request cloud services. So long as you're willing to pay, you can become a customer of that cloud. Okay? So it's a cloud service that is available to the public or application developers. Okay? So there's one flavor of cloud. Okay? Then you can have something called a private cloud. A private cloud is essentially a cloud that is run by an enterprise for its own users or employees. Okay? So it's not open to the public. So the only users of that cloud are essentially the employees of that enterprise that set up that cloud. Okay? So for all practical purposes, it offers the same functionality as a public cloud. You can get infrastructure resources, you can get platform, you can even host SaaS applications on it. So it has the same functions, but it is designed for a single enterprise. Okay? Maybe it's a large company that has lots of users, so they set up their own cloud platform. They don't go to Amazon to buy resources, they set up their own. And it essentially offers the same functionality as whatever I've been talking about. Okay? That is called a private cloud. Okay? And now you have something that's a mix of the two, which is called a hybrid cloud. Okay? In a hybrid cloud, some resources might be on a private cloud, which is a private data center owned by the enterprise. Some of your resources might be on a public cloud, which could be an Amazon's cloud or Google Cloud or Azure. And essentially what you're offering to your users is some mix of the two. From the user's perspective, it shouldn't matter. Okay? Because your code is running on some server. Why does it matter whether it's a server on a public cloud or a private cloud? They look like servers that run code. Okay? But from an enterprise's perspective, having a hybrid cloud is advantageous for the same reasons I had mentioned when I talked about enterprise data center. Right? Because you can set up a private cloud that will run on your data center. So you have to decide when you set up your private cloud, how large should your cloud be? Okay? What is the peak capacity you want? Okay? And then you have to provision that many resources. And often your average utilization in any data center is much lower than the peak capacity. So lots of servers are sitting there idle. Okay? So if you have a very large amount of peak capacity, you will have lots of idling resources. Okay? And you will occasionally use that peak capacity. But if you have less peak capacity, you might have a scenario where lots of users make requests for instances, you run out of capacity. Okay? User says, give me an instance. Cloud says there is no server available. Okay? Users don't want to hear that now, they can't run their code. So what do you do in this case? Okay? You don't have resources on your private data center or your private cloud. Okay? So this is where you can use a hybrid cloud. Okay? So hybrid cloud says if you have resource pressure on your private cloud, then you can overflow into the public cloud. You can dynamically go to public cloud, get some instances, and then hand them to your user. Okay? So essentially, your cloud is now spanning both a private and a public cloud. Okay? Is that clear? So this is how modern enterprises will actually use cloud resources. I think last time there was a question saying, can you have a mix? This is that mix. Okay? You will have your private cloud where you have your more critical applications. Some applications you can essentially move them to a public cloud or overflow into a public cloud on demand. Okay? And get the flexibility of both worlds. Any questions on this before we move on to some other quick things? Yes. Yeah. So the question is, there's a term here, cloud bursting. What does that mean? So cloud bursting essentially is a technique where you overflow on demand into public. Okay, so whenever your private cloud comes under pressure, okay, your resources burst into a public cloud. So that's a term that is used technically, but it's essentially overflowing into a public cloud. Okay. So very quickly, what kinds of cloud workloads do you see on these platforms? Anything you can run on a data center on large servers are an example of a cloud workload. So you have client server workloads of all kinds, web services, databases, content delivery networks, and so on. Okay, those are interactive services, interactive class of workloads, request response style workloads. Okay, you can have batch processing. So batch processing is anything that essentially runs as a batch. Okay, so you run periodically, run a batch job. So you can do payroll or night processing of work and things of that sort. So those are all batch work. Okay? So also another popular class of cloud workloads. And there's something in between, which is data processing and analytic workloads. So these could be large databases that have transaction processing and things of that. Okay? Anything that requires large databases and you can do analytics on it, those are data processing workloads. And the final class is what you probably are somewhat familiar with. Those are all AI workloads or workloads for AI application. Most of them are training oriented. You can also have inference, but a lot of them essentially have to do with training. Okay? So different classes of application, different mixes. Okay? So everything from interactive, batch, data intensive to AI. Okay? So if you look at any large cloud platforms, you will see this mix of applications running on that platform. And then the cloud platform has to make decisions of which physical machines to use for certain class of workloads. Okay? Is it okay to have one VM running a web service, and on that same physical server, you run another VM that's doing machine learning training? Okay? Does it even matter? Now, there is research that shows that although virtual machines provide you isolation, okay, but if you have very good isolation, it shouldn't matter what else is running on that server, okay, because you're isolated from whatever else is actually running. But in practice, it turns out not to be the case, okay, because at the end of the day, on the hardware is shared. So you might have things like caches that are shared across virtual machines, okay, because you cannot actually partition things like processor caches. Okay. So you might have some interference, some mild interference between workloads simply because there is no such thing as perfect isolation. Okay. So that essentially has become an area of research where you say, how do I take all these workloads? How do I map them on different machines of my cloud? How do I ensure good isolation, ensure that my machine learning training is not impacting the latency seen by my web services, because users care about latency, batch workloads care about throughput. How do you optimize all of these mix of work? Okay, so these are all interesting research questions. I'm not going to go into them here. Just wanted to give you some sense of what all things do you have to worry about when you build a cloud platform. Okay, one of them is, how do I decide which workloads run on what machines, as an example. Okay, so very quickly, we'll talk about storage, because we mostly spoke about virtual machines and instances, but a lot of the cloud platforms, not a lot, many of the cloud platforms also offer rich storage services, okay? Because your application either needs machines to run on, and it needs storage to keep its data. Okay? So you probably know about storage clouds already, but even though you may have never used a virtual machine in the cloud, you probably used Google Drive and OneDrive and Dropbox. All of these are examples of storage clouds. Okay? So the cloud is essentially giving you some storage that is kept somewhere else, and you can keep your documents, photos, whatever you want in that cloud. Okay? It's used for both backup as well as keeping data of various kinds. Okay? Now, there are different flavors of cloud storage depending on what type of data you want to keep, how critical it is, and so on. Okay? So I'm going to go through some examples. So one is called object storage. Okay? In object storage, essentially, you keep large blobs of data on a storage platform, and you have a get and a put function that allows you to get that data or put data into that object. Okay? So this is very different from file systems. Okay? In file systems, you all know what file systems look like. You have one on your machine. Your files, there is hierarchical namespace. You can create files using names and so on, and you read and write files. Okay? That's file storage. Okay? Object storage is a very different class of storage, which is used for large amounts of data. Okay? In this case, your data is viewed by the cloud provider as some large chunk or large blob that you can access not using read or write, but using gets and puts. Okay? Get essentially allows you to get an object from the storage, and put allows you to put the object. What the object is opaque to the cloud provider. You have to decide as an application provider what you put in an object. Okay? An object would be a large archive, which is a backup of all the files on your machine. That entire backup archive could be one object that you kept in this object, just as one example. Okay? Or it could be a large photo library. Okay? So that that blob has lots of individual files which are not visible to the cloud provider. You only have to get the object and you access it back. Okay? So that's object storage. You can also get block storage. Okay? When you get a machine on the cloud, it's going to have a disk attached to it. And that's where it's going to have its OS files. You can create files and so on. So that's essentially standard block storage where you can create a file system. Okay? That's very standard offering. Okay? You can get file storage. What that means is the cloud provider will create a file server for you. Okay? And then you can essentially store files on that file server. You can mount those volumes remotely and so on. Okay? So you can get file storage from the cloud provider, and then you can get archival storage. Archival storage is data that you want to keep for long term, okay, but it's not accessed frequently. Okay? So basically, it looks like file storage, but it is essentially created on very inexpensive disk, so that the cost of archival storage is much cheaper than something like file storage. Okay? Because you're storing large amounts of data, you might not access it for years. You don't want to pay a lot of money for it. You want it at cheap. So they can essentially have cheaper disks that are used to keep your archival storage, and you can get maybe better or faster disks for your block storage or file storage. Okay? So different types of storage offerings from cloud providers. There are many cloud providers, Dropbox, you probably know Dropbox, Google Drive, OneDrive Box, and so on. And then there are all kinds of backup services that also use essentially cloud storage to keep all your files and so on. Okay? Any questions? Yes. Okay. Question is, can we say that object storage or blob storage is a key value abstraction on top of file storage? So first is, an object storage is a key value abstraction because that blob has a handle, which is a key. Okay? And when you specify that handle, you'll get that entire object. Okay? So it is a key value stored. Now, how is that stored internally? Is it stored on file storage? That depends. Okay? In some cases, you can use an underlying file system to create a layer which exports an object storage to its users. In other cases, you can actually construct an object storage using the OS, and it's essentially not using a file system underneath. That's an implementation detail, okay, as to how you are essentially using that object storage to actually store data on this. The simplest approach is you can use a simple file system and layer the object storage on top. But there are many that will not do that for efficiency reasons. They'll take a disk and they'll write their own object storage software on top. So both of those are seen in practice. Okay. Other questions? All right. So now I want to spend a little bit of time talking about Kubernetes and cloud orchestration, and then we will be done with this topic on cloud computing. Okay, so what is cloud orchestration? So that's something we have to understand before we get to things like Kubernetes. Okay, so as you can imagine, okay, when you have a large cloud platform where there are lots of users coming in and asking for servers, asking for storage, and then saying, I'm done with this, relinquish my server, and so on. Okay, so you have to ask, who is actually responsible for processing all of these requests and deciding which server or which VM gets allocated to which user and so on. Okay? So there's some sort of control logic that has to do this. There has to be a control plane or a management plane that is responsible for deciding how resources, how users get mapped to machines, how applications get placed onto machines, and so on. Okay? That controller is responsible for what is called orchestration. Orchestration is simply the process of taking a bunch of physical resources and then allocating them out as virtual resources. Okay? So you're essentially orchestrating the resources on your platform by allocating them and sharing them across users. Okay? So this control plane or this controller is essentially doing orchestration. Okay? So customer requests for one or more instances come in, the orchestrator says, okay, you want a large instance, then you have to figure out which physical server has enough idle capacity so you can spin up a new VM on it. Okay? So that's essentially a problem of virtual machine placement. So you have to decide which server is going to be used for it. Once you allocate that server, you have to now automatically create a virtual machine. You have to now configure the network for the virtual machine. You have to allocate some storage and attach the storage to the VM. Before you can allocate all of that, not allocate, but make it available to the user, all of these steps have to happen in the background. Okay? That controller is performing all of this for you. There are no users who are sitting there and saying, customer came in, let me type some commands and spin up a new VM. All of this is automated, right? Because there are thousands and thousands of users, so everything is completely automated. So all of this is being done essentially by this cloud orchestrator. Okay? So it's a large management plane that is sitting essentially above your servers and storage and deciding how to configure it for various users, how to then relinquish resources and things like that. Okay? So most of these IaaS platforms now use this cloud orchestrator. Okay? They support both virtual machines and containers. Okay? So you can essentially ask for a container or you can ask for a virtual machine, and that the orchestrator is going to take care of all of this placement and all of that for you. Okay? So that's the background on cloud orchestration. What I want to do is essentially go into a case study of an actual orchestrator, which will be Kubernetes. Okay? Before I do that, is there any question on what cloud orchestration means? Okay. So let's talk about a very popular open source cloud orchestrator, which is Kubernetes. Yes, many lectures back, we talked about Borg, okay, which was Google's scheduler for their data center, if you remember. Okay, when we were talking about distributed scheduling, I talked about Mesos and I talked about Borg. Okay. So Borg, one way of looking at Borg is it was Google's orchestrator for their machines. Okay. Then they essentially made an open source version of it and made it available. Okay. So, and that version is called Kubernetes. And Kubernetes essentially inherits a lot of what you actually saw in Borg. It has similar ideas. Okay. It is a container orchestration system. It was not designed to do VMs. You can have other orchestrators that do VMs or both VMs or containers. Kubernetes at its heart is a container orchestrator. But that's an orthogonal issue. You're still essentially allocating physical resources as virtual resources. Okay? So first thing is Kubernetes, because it derives a lot of its concept from Borg, is designed to handle very large number of servers. So if you remember, Borg was dealing with tens or thousands or hundreds of thousands of servers. It could manage very large clusters. Kubernetes is also designed to scale to a very large number of instances. Okay, so it is based on Borg, and there is a successor to Borg called Omega, okay, which is the next version of Borg. And Kubernetes essentially has both of those concepts built in. Right? So in addition to deciding which containers run on which machines, Kubernetes can do all kinds of other things for you. It can replicate your application on the fly. You can say, I want to run this code, and it needs to run on 5 machines or 5 containers. It will create all those 5 containers for you. Okay? It will automatically load balance across your replica. You can just send requests to your service. It will take care of deciding which requests go to which replica and which container and so on. It has that capability built in. Okay? It can do automatic scale up or scale down. You can specify when you deploy your application on Kubernetes, saying this application needs to run on anywhere from 2 to 7 machines. You specify that range. Okay? Kubernetes will automatically decide how many machines, or in this case containers rather, to allocate to your application. If the workload goes up, it will keep adding containers until you hit the upper limit. The workload goes down, it will start scaling things down until you come to a lower limit. So it's like a thread pool, if you remember. You can essentially spin up new threads or shut down threads. Here you're doing the same thing with containers. Okay? So it can do all of that. It has automatic failure detection and restart capability. If your code crashes, okay, it will detect that some container has gone down and it will restart your that code on a new container somewhere. Okay? So it has failure handling. So users don't need to worry about that machine crash. I need to restart it. It will do all of that. So these are all features of an orchestrator in addition to the base feature of deciding which machines some application runs on and so on. Okay? Load balancing, replication, scale up, scale down, self-healing features. All of this is built into this system. Okay? So let's look at a little more details of how all of this is done. Okay, so here are some concepts to keep in mind. The first one is called a pod. In Borg, you had this concept of a cell, if you remember. Okay? In the Kubernetes world, a cell is essentially a pod. A pod is a slice of a machine. Okay? It's an abstract slice of a machine that runs all the containers of a single application on that machine. Okay? If there's some application that's deploying some number of containers, they'll be deployed in one pod on that machine. Okay? So these containers within a pod can see one another. Okay? And there may be another pod on that machine. So pods cannot see inside one another. Okay? But pods can see whatever is inside it. So in this case, there's an example where there's a pod with 2 containers. These 2 containers can actually talk to one another. They can see each other's IP address and communicate and so on. But if there's a second pod, if that belongs to some other application, that's isolated from this pod. So it cannot actually even see the address space of this pod and so on. Okay, so pods are your granularity of allocation. So that's the smallest unit of allocation. Okay, when you have a distributed application, you will have multiple components. Okay? You have to decide as a developer how your components essentially map into pods. Okay, so let's say you're doing a microservice. Okay, you're doing one for lab 2. Right? So you have 3 microservices, right? So you can say each microservice goes inside a pod. That's one architecture. Okay? So when you deploy this in Kubernetes, Kubernetes will spin up 3 pods. Inside each pod will be one container, and inside that container will be the code of your microservice. Okay? It's one architecture. You could say, that's not how I want to do it. I want to essentially have one pod for my front end. Okay? And another pod that has both of my backend. My ordering and catalog are in one pod because they might share a database. In this lab, you don't, but assume they share a database because all the data is persisted into a database. So you can put both of those containers in its own pod. Okay, that's another architecture. But you as an application developer have to decide how you want to take your code and split them into pods and containers. Okay? And in addition to that, you can say that my front-end service can be scaled from 1 pod to 10 pods. Okay, so then if the code sees more requests, additional pods will be created and containers will be spun up, and now you're 10 replicas, okay? Up to 10 replicas. So you can now scale each of this independently. Yeah, your question? Yeah, the question is, can pods span across multiple machines? Pods will absolutely span across multiple machines. This picture is only showing one machine, but there are thousands of machines. Each machine will have 1 or more pods. Each pod will have 1 or more containers. Each pod has to have at least 1 container. At a minimum, each container has its own pod, but as this example shows, you can have more than 1 container if you want to put multiple things in a pod. Okay, so yes, every machine will have some number of pods, and the pods will span multiple servers. Okay, so So that's what is said here. Pods of an application will span clusters of a machine. And the interesting thing is when you create an application, Kubernetes will create a network for it automatically. So all the containers of that application can see one another because the network is created for it. Okay, so you get your own IP address space, a private IP address space, where these containers can see each other and talk to one another, even though they are on different machines. Okay? So each application gets its own network space, which is why there's something called a pod network. That is your communication backbone. That's essentially a private network that's constructed for a particular application. And all pods are connected to that network. So all containers in your application can automatically talk to one another without the user doing anything specific. This is all happening for you as part of the orchestration framework. Okay. All right. So that's Kubernetes. Now, the other concept beyond pod is something called a service. Okay? So service is how application is exposed to external users. So service typically will have a public IP address. Okay? Pods have a private IP address and they're part of the pod network. But if it's a private IP, a user cannot actually send requests to that machine because it's a private IP address. So to expose the application to the external world, you create something called a service and you assign an IP address to that service. Okay? And now that application is exposed through that IP address, so you can now send requests to that service. And a service is essentially like a load balancer. It can then take requests that are coming in and then split them across replicas if there are replicas. That don't have to be. Okay? So in this case, you will see that there are two hosts. Okay? Those boxes are essentially pods of different applications. So they're mixed up on each host. Okay, but there is this service that has 3 pods that it has replication factor of 3. So you'll see it has the same label, some production service. So this service receives requests and then it forwards them to one of these 3 replicas. That replicas essentially are all running the same code. Okay, so it is doing load balancing across these replicas. Okay, that's also done automatically for you. Okay. Now, in the simplest case, you will only have one pod. There's no replication for your application front end, and there is a service that's just going to send requests to your front end. There's only one copy of the front end. That's the simple case. Okay. But in this case, you have replicated your front end. Okay. This question. Okay. Question is, when you say replication, are you talking about replicating containers or replicating pods? But in the Kubernetes world, you deal with containers. Because as I said, the smallest granularity of allocation is a pod and not container. Containers are inside a pod. Okay? So you are going to replicate pods. You're going to create pods. The simple one-to-one mapping says each pod has only one container. So then it doesn't matter. It's the same thing. But you deal with, Kubernetes deals with pods. Pods contain containers. The simplest one is you just have one, but as I said, you could have packed more than one. Okay, so you are going to replicate in granularity of pods. Yeah. Yes. The question is it possible to run database inside a pod? So pod is essentially going to allow you to run a container. You can run whatever code you want inside a container, including a database. There is no restriction on what you actually run inside a container, right? Because it's any application. So you can certainly run database applications because your application will have backend services also. If you're backend tier, that will have to run a database, right? So then you will have a container inside a pod having a container. The container talks to a database. Okay? Remember that a database is somewhere on disk. This is just the container. But the container will run the database server that will actually access data from a database. Yes. Okay. Question is, I haven't actually talked about all the details yet. So it says that each cluster has a static IP address. So what services do is that they have a static address, okay, and typically it can be even a public IP address that is exported. Okay, the pods network is private, and that can change because pods are essentially ephemeral. Okay, pods can crash, pods can be moved, and so pod IP addresses can change. But from an outsider's perspective, none of that is either visible or doesn't matter, because you are dealing with a service. The service is the abstraction that's exposed to you. How the service maps requests to pods is an internal detail that Kubernetes is doing. Okay? So essentially what you want is the service to have a stable IP address, and not just stable, but often a public IP address that is not going to change. Okay? Even though pods might crash, pods get replicated, pods get shut down, so the number of pods might change, so all the IP addresses will keep changing, but the service IP address will not change. Okay? So pods are more transient. Okay? A service is more permanent. Until you shut down the entire application, service will stay. Pods might come and go depending on what's happening, how you're replicating, and whether things crash, you restart them somewhere else. All of that is dealt with internally. Okay? Because this is doing a lot of extra orchestration, some of these concepts which you may not usually face are automatically dealt with. Okay? Normally, you would have gotten 3 machines and put these 3 servers and you deal with them. So they don't come and go. They actually have stable addresses. In Kubernetes world, that is not the case. It's doing load balancing, replication, all kinds of things for you. Okay. All right. So a couple more things, then we will stop. So here is the control plane. Yes, your question. Okay. Question is, do we call Kubernetes as a platform? So Kubernetes is actually an orchestration platform. It's not a platform as a service per se, okay? Because it is essentially, at the end of the day, allocating containers. It doesn't decide what is going inside the container. In a platform as a service, you have to worry about the application runtimes and things of that. So this is giving you containers. What goes in there as a container, you have to package. Like you can make a Docker container and put it into Kubernetes. So it is something that is more closer to an infrastructure cloud than it is to a platform cloud. Although, as you can see, there are some elements of application level services of replication that are built into Kubernetes, even though it's doing something that's much more basic. Yeah. Okay, question is, does Kubernetes decide the replication strategy, or does the user or the developer get to decide? So whenever the developer deploys an application to Kubernetes, you have a config file. And in that config file, you specify all the details, saying this pod can be replicated, this is the replication range. This pod should not be replicated. So you specify all of these things. And then Kubernetes will just perform whatever is told. It's not going to automatically replicate things without it being told to. Okay? Yes. Okay, question is, Docker and Kubernetes do similar things. Which one should you recommend? So actually, they are not similar. I'll show you an example of what Docker does and what Kubernetes is. So Docker is more of a packaging set of tools. It allows you to take code. It allows you to containerize it. It makes it portable. So once you containerize it, you can distribute it and so on. Okay? When you want to deploy code, okay, specifically if you want to deploy code on a cluster, okay, Docker will talk to something like Kubernetes. So Docker and Kubernetes now work closely with one another. So Kubernetes is the platform where Docker code can be deployed in a cluster setting. Okay? You can also get Docker for your own machine, which is what you did, right? When you did the lablet, you just deployed Docker on your own machine. You are not running Kubernetes at that point. That was just a single machine deployment. But Docker is fully capable of taking the exact images you built and deploying it on a large cluster. And in that case, it's going to use Kubernetes as the framework to do that. Okay? Now, having said that, there was a time when Docker had its own container orchestrator, which was called Docker Swarm. Okay, some of you may have heard of Docker Swarm. Docker Swarm and Kubernetes are essentially competitors. They did more or less similar stuff, but Kubernetes became more popular. Docker Swarm didn't. take off. So I think it still exists in some shape or form, but not used widely. So Docker has basically gone and said, we will now make Docker images compatible with Kubernetes. So think of Docker as a way you do the development, and packaging Kubernetes as a way you actually run in production, right? So that's how you deploy. So Kubernetes is that part of the equation. So they will work together. Any other questions? In fact, there will be a Kubernetes lablet coming soon. So you can go and play with some of this stuff. All right, so control plane for Kubernetes. There are many components that are in here. I'm not going to go into a lot of details. There's an API server, which is a REST interface. Okay, this is not the REST interface for an application to send requests. This is the REST interface for you to make calls to Kubernetes and say, spin a new container, or here is a new application, go deploy it, things of that sort. So it's an interface for doing the management. Okay? It's a control plane interface. Okay? So that's your API server. Okay, so then all of the configuration in Docker is essentially stored in a key value store at CD. What the key value store is not important, but what is important is that key value store has all the information about what is currently deployed. This is the state of the cluster. Okay, what is deployed, where is it deployed, what's the replication being done. All of this information is essentially stored in this key value store. Now, if you remember when we were talking about Borg, I said Borg is designed to be highly fault tolerant. So it takes all of its database information, replicates it 5 times. Yeah, I think you may remember something like this. Okay? So that component in Kubernetes is etcd. Okay? So it is, as a result, highly replicated. Okay? It uses consensus protocols. Basically, it uses Raft consensus. We haven't gotten to consensus yet. We will get there. But consensus allows you to take essentially multiple copies of this key value store and ensure that they are all consistent. If you make change to one, all of them see that change. That way, if one copy of the key value store dies because the machine that it ran on essentially died, okay, your cluster as a whole continues to run. Because you don't want the control plane to go down. The control plane goes down and the cluster will go down. You can't actually make any operations on it. And the data or the state of the control plane is critical to maintain, which is why it is stored in a highly durable key value store that's replicated, kept consistent with one another, and so on. Okay? So that is where you keep all of your data for the cluster. Okay? Then there is a controller manager that's essentially responsible for starting pods, replicating pods, and so on. Okay, there is a scheduler. Okay, the scheduler is responsible for deciding when a new application comes in, which machine to run it on. This is equivalent to our cluster scheduler. If you remember when we were looking at batch scheduling, okay? So a job comes in, you have to assign that to some idle nodes and so on. That work is being done by the scheduler here. Okay, here we are not getting batch jobs. We are getting requests to spin up new containers, or pods rather, not containers. So that scheduler is going to decide this pod needs so much resources, which machine has those resources, where can I start it? Okay? So that's the job of the scheduler. Okay? And then there is essentially a cloud controller manager. Okay? So this is the component of Kubernetes that will talk with a native cloud. Okay? You can deploy Kubernetes on your machines, or you can deploy Kubernetes on a public cloud. Okay? If you deploy Kubernetes on a public cloud, Kubernetes has to itself go and get machines so that it can spin up containers. Okay? So this is the component that will talk to Amazon or Azure or Google so that it can get machines on the fly and relinquish machine so that whatever work is coming in, it has enough machines to essentially use for those applications. Okay? Lots of different components. I think the main things really are that etcd key value store, the controller manager, and the scheduler. Okay. All right. So 1 or 2 more things, then I think we are done. So this is what that was the control plane. This is essentially a worker node. Okay. That's what a machine in that cluster is going to look like. So you will see that that machine has some number of pods. In this case, there are 2 pods. There are yellow. Those pods will have actual containers in them. There's something called a proxy. which is going to deal with all the networking and the load balancing requests that come in. So they come into the proxy is going to forward them to the pod. Okay, and then there's a control node, not a control node, control agent running on each node, which is called a kubelet. Okay, that entity is what is talking to the control plane, that the plane that I showed you earlier. Those two talk to one another. So this handles the management. Okay, and there's a container runtime that handles the execution. Okay, so this is your data plane, that's your control plane. Okay, so the container runtime is responsible for essentially starting, stopping containers, and so on. And kubelet is going to receive commands, which is going to pass them on to the container. Okay, lots of various parts, but I think hopefully the high level picture is clear. Yes, question. Okay, that's a good question. So question is, a node is a physical machine. Okay, so if you have physical machines, why did you not deploy containers directly on the physical machine? Why do we need this pod abstraction? That's the question, right? So that's a good question. Actually, I think it's worth thinking a little bit about this. So the reason you need a pod is if you put all containers on a physical host, let's say. Okay? Remember that the containers can belong to different applications. In a cloud setting, they could belong to totally different users. Okay, so some random user comes, asks a container, it gets put on this machine. I go put my container on that machine. The containers could potentially see one another. Okay, you don't want that to happen. So you want containers of each application to be isolated from what else is happening on that machine. Okay? To do that, you create this logical machine abstraction called a pod. It's not a virtual machine, but you can think of it as some sort of virtual machine where you can't see outside that virtual machine. So it's essentially a sandbox, okay? Not a real virtual machine, but a sandbox where your containers can essentially reside, see one another, and communicate with one another, but you don't see what's happening elsewhere. Okay? And the whole reason for this is because this physical node can be shared across multiple customers or multiple users, and you want to provide some isolation. Okay? If you didn't need that, okay, then you didn't need the pod abstraction. You could just deploy your containers. Containers themselves have isolation. Remember, they're still lightweight virtual machine. That may be good enough. Okay? But if you want this additional isolation where you want to prevent applications, not containers, but applications which are multiple containers from not seeing other containers, you need a pod. Okay? Yes. Okay. Question is, we have things like C groups and namespaces that allow you to isolate the processes within a container. So how can processes from one container see another container's process, right? Okay. So maybe I need to rephrase. When I say a container can see one another, what I really mean is a container can communicate with something else that's inside the pod. Okay? You may or may not actually see processes that are inside that container if they are part of a different namespace. Having said that, all containers across pods are actually part of a larger namespace. Okay? There's a container namespace that isolates processes. There is now an application namespace that isolates all the containers that are across all the pods. So there are two namespaces, but when I said you can see one container can see one another, it just means that its ports are visible to me. I can communicate with it, things of that sort. So I can have this process make an RPC call to that process, and the networking rules will allow me to do that. There's a third container I will not be allowed to, because I'm not allowed to access any of its processes. That's what we mean by when you can see something. Okay? Yes.
So we usually have a when we talk about data center, it's the like proxy request coming in.
Okay, so are you talking about traffic? You're talking about traffic management, right?
Yeah, like how does it balance?
Yeah. So question is that how does Kubernetes deal with higher level traffic management in a data set, right? So you should think of this as layers of abstraction, right? So there's a network infrastructure for a cloud data center. It has some traffic management rules. There are all kinds of firewall rules and so on. Okay? Now, whatever you have as one application is subject to those rules. Okay? So you can essentially take your Kubernetes rules and connect it to data center rules, okay? Which we did not worry about here. We just assumed that Kubernetes was managing the entire set of resources. But if you have higher level policies, those would be at a different level of abstraction. Kubernetes would sit on top of that, and it would have to somehow interact with it depending on what those rules are. Okay? So in some sense, so you can ask that same question for virtual machines as well. At if I have a set of virtual machines, how is traffic management play a role in deciding how those work? When you do have to then essentially use VLANs and then put VMs in a VLAN and then associate traffic rules. So there's a whole set of networking stuff that's going to happen underneath, which we did not talk about here. All right. Any other questions? Yes. The question is, the reason why are we using a pod instead of a VM? Yes, a pod is essentially not a real thing. It's just a set of rules that sandbox you. It's not like a virtual machine which requires an operating system or anything like that. It's a set of containers that have their own encapsulation. A container is an encapsulation. You put a bunch of them together with another encapsulation. So that's a pod. So it is another way to draw a sandbox. And it's a much lighter weight than virtual machines for sure. All right. So one last thing, which is container D. Okay, so container D is what Kubernetes uses to actually start and stop containers. Okay, so it will make all the policy decisions, but then at the end of the day, there has to be some framework that you use on Linux to actually say start a container, stop a container. Okay, so that is what container D will do. So that's the most lowest layer of Kubernetes as your container runtime that sits on each machine. That was this orange framework here. So this is what your kubelet will use to say, okay, start 2 more containers and put them in a pod, create a network that puts them in a pod and things of that. Okay, so this is your low-level container orchestration framework. Okay, this is itself a non-trivial component. As you will see, it's an open source framework, but you can see that it has a whole bunch of these components. It uses gRPC for communication. It has a way to collect metrics for CPU usage and so on, reported back to Kubernetes. It can deal with images, which in this case would be Docker images and so on. Okay? So that's your lowest level that you are using within Kubernetes for Kubernetes to start, stop containers and so on. Okay? And this is not actually part of Kubernetes itself. It is its own open source project. Okay? And it is used by many cloud providers as their container runtime for offering Kubernetes-like service. So if you go to a Google Cloud and ask for containers to run your application, underneath it is using container D. It may not use open source Kubernetes, but it will use their own version of Kubernetes that they have built for their purpose. Okay? And because Kubernetes is open source, you can take it and make your own version of it. So all these cloud providers have essentially a Kubernetes-like container service. Okay? Underneath, they all use container. Okay? But the actual Kubernetes is modified for each of their own use. Okay? So that's it on orchestration. We have maybe 5 minutes. I'm going to start another topic, but let me pause to see if there are any questions. Yes. Okay, this question. Yes. Yeah. So this figure is actually misleading. This figure is from internet, but I didn't draw it. But I thought that it was actually misleading. So technically the container, so that green thing says container, but that's really, the containers are technically inside the pod. Okay? So it should not have said containers. That should have just said a container runtime pod, and the container should have been inside the pod, because the pod is what is encapsulating the container. This figure makes it look like the containers are encapsulating pods. Incorrect figure. I think I should throw it out next time. Yes, so I think that if you ignore this green thing, everything else is right, and then containers are actually, you can think of them as boxes inside a pod. Okay, and then the runtime can work with those containers. Okay, anything else? All right, so let's just spend a few minutes. The next topic, I'll just do some quick introduction to what is coming next, and then we can stop for the day. So we are done with cloud computing. The next several lectures are going to look at what I would call classical problems in distributed systems. So we are going to look at a whole bunch of them. Today I'll maybe spend 2 minutes talking about the first one, which is clock synchronization. Then we'll talk about leader election. We'll talk about mutual exclusion, which is distributed locking, distributed transactions, deadlock detection. We'll talk about the CAP theorem and so on. So this is essentially, you should think of these as foundational concepts that you will use in lots of different scenarios when you write distributed applications. So far, I think the only things you have used are things like locks and concurrency and thread pool. But as you write more complicated applications, you will have to do things like reader election, you will have to do consensus, all these concepts that you see in larger systems. Okay? So the next few lectures are essentially going to look at these principles, okay, of how do you build large-scale applications, what are the things you need to know. Okay? So let me spend maybe 2 minutes talking about the first concept, which is time ordering and clock synchronization, and we'll continue this next time, but let me just introduce this topic. So all of you know what a clock is. Okay? So in this topic, we are going to look at algorithms to take clocks that run on different machines and synchronize them with one another. Okay? So that the clocks all essentially have the same time. Okay? So first, let's ask, why does this matter? What is this problem of clock synchronization, and how is it relevant to distributed systems? Okay? So to understand that, you have to understand why this concept of time actually matters in a distributed system. So if you think about distributed systems, you will think about services. There are requests coming in, responses going back. Each of them can be thought of as some event that is occurring in your distribution. A request arrived, a reply went back. Those are all events. Okay? And events occur at certain points in time. Okay? Now we'll see that there are many systems where you actually have to worry about at what time certain events occurred or in what order certain events occurred. The order sometimes matters. Okay? If you want to understand the order in which something happened, you have to assign timestamps. Right? So you have to assign a timestamp, and then you can compare the timestamps to say what order did this happen. Okay? Now, if you have one machine, this is a trivial problem. Okay? You can timestamp whatever you want with whatever the clock on that machine says. Okay? And then you can compare timestamp. But in a distributed system, there are not one, but many machines. Okay? And each machine has its own local clock that is telling you what the time is. The way your machine or your phone tells you the time is there is essentially a chip that acts as a clock. Okay? It's essentially ticking. And then your machine can then look at that hardware chip and say, this is the current time. Okay? So every machine has a clock built into it. Just as your watch has essentially a chip that allows it to tell the time, so does your computer. Okay? Now, if your machine clocks are not synchronized, and then you take timestamps and compare them, then it is not very meaningful to compare time if the clocks are actually not synced with one another. Okay? So maybe your machine clock is running 10 minutes faster than real time. Okay? So if you look at the timestamp it is assigning, that's not really the time at which that event occurred, right? Because your machine clock is actually off. Okay? So you want to make sure that when you want to compare timestamps in a distributed system, because these timestamps are being derived from local clock on the machine where that event occurred, and you want to now compare them across machines, you want the clocks to be synchronized. Otherwise, the whole problem is not going to make any sense. Right? So that is why clock synchronization is a very fundamental, basic building block in any distributed system. If the machines are not synchronized, a lot of issues are going to crop up because you will not be able to compare things. Okay, so here's a very simple example, and I'm going to use that and stop. That tells you why clock synchronization matters. Okay, so this is an example where you are essentially using two machines, one maybe to do some development and another machine to do your build, which is compile the code. Okay. Now, the way all these build tools work, if you understand Make or any of these build tools that you have, Maven and things of that sort, they basically use timestamps. Okay. So they will only do incremental builds, only things that have changed as rebuilt. Okay. When you say Make or whatever, call Ant, Gradle, it will essentially only recompile code that has changed. How does it know what has changed? Right? It is going to use file timestamps. It will say this file was built previously at this time, and now the timestamp is newer, so the user changed the code. Okay, so that file will get rebuilt. Okay? If the timestamp is older than the most recent build, it will not get rebuilt because it is actually not, based on these two timestamp comparison, it hasn't changed. Okay? Now, if you take a machine where the two clocks are not synchronized, you might have problems because you might modify some file and you can save it to the build machine. And then if the clock is off, it might actually get an older timestamp than the previous build, just as a hypothetical example. Right? So now if you call build and you compare those two times, even though the file has actually changed, the timestamp you gave is older than the build time because your development machine has a clock that is running much slower, let's say. Okay? So your Make tool or the build tool will get confused and not rebuild yours because it will think it's not changed. Okay? And then your code will have some strange bug and you won't understand that you changed the code, but the code is not reflecting your change, something like that. Right? So there's a very trivial example, but it shows you that timestamps are fundamental in many types of systems. They're used to make all kinds of decisions. So if you don't have accurate timestamps, lots of other things will go wrong. Okay? So now to solve that problem, we have to make sure that there are all these machines that are part of your network, their clocks are going to run in sync. Okay? You don't want some clock to run faster and some clock to run slower, because then those timestamps cannot be compared. Okay? So that is the problem of clock synchronization, and how to do it we'll talk about next time. Okay? So let's stop here today.